In this segment, we talk about the important idea of mixture models. Suppose that we have n independent events. They're independent, but they're not identically distributed. In fact, it turns out that each event is drawn from one of two distributions. So in the univariate case, it might be the red distribution here or the blue distribution here. Now all we're given is the positions of the events, that is to say the values of x shown by these purple dots here along this line, or if it's not just a univariate distribution, if we're in multiple dimensions, what we're given is the value for each event of its vector position, x sub I here. Now we don't know which distribution the event is drawn from, but we do know for each value of x along the line here, or multivariate vector x here, we do know what the respective probabilities are of it having that value of x if it's drawn from distribution 0, and we call that P0I, or if it's drawn from distribution 1, and we call that P1I. And it should be obvious to you that this will generalize to more than two distributions. What we want is an assignment of each event. Did that event come from distribution 0, or did it come from distribution 1? Now we're never going to know for sure, of course, so that assignment is going to just be probabilistic. What's the probability for each event that it came from each distribution? We're Bayesians again, so we're going to do this by building a forward statistical model. And you'll recall that a forward statistical model starts by assuming that you know everything there is to know about the data, and then writing down what is the probability of seeing exactly the data set that you saw. So, although we want to find what the assignments are, we're going to assume that we know the assignments. And let's let this vector v, which is a bit vector, a vector of ones and zeros, say what the assignment of each event is. So if the vector v were this particular vector of ones or zeros, that would say that event 1 is from distribution 1, event 2 is from distribution 1, event 3 is from distribution 0, and so forth. The other thing that we need to know about the data to construct a forward model is what's the a priori probability that an event chosen at random from our set will be from, say, distribution 1. That is to say, we want to know the probability that an event vi is drawn from distribution 1, averaged over the vi's, so that that's just going to be some number s. In other words, that's the fraction of events in distribution 1. So back in this picture, that has something to do with the ratio of the area of this blue distribution to perhaps the total areas of the two distributions. Well, that's everything we need to know to write down a forward model for the probability of the data. What is that model? The probability of the data given the parameters, and now the parameters are the vector v and the scalar value s. And to get exactly the data we see requires that for every event that's drawn from distribution 1, an event with probability p sub 1i, and for every event drawn from distribution 0, an event with probability p sub 0i, and since these are all independent, we simply multiply the respective products together, and that's the probability of the data. It's interesting that S doesn't actually enter this formula. S enters it implicitly as something that will affect how likely it is that we'll get a certain number of factors here versus a certain different number of factors here. But it doesn't enter directly, so S is what's called a hyperparameter. It affects the distribution of the v's, but it doesn't explicitly enter the formula for the data. So now we do the Bayes thing. We want to know the probability of the parameters, v and s, given the data. That's proportional to the probability of the data times the prior on the joint probability of v and s. Now, because this is a joint probability, it's going to be useful if we write this out as this product of conditional probabilities here. So that probability of V and S jointly is the same as the probability of V given S times the probability of S. Can you see now how S is going to enter? Because the probability of any given V is going to depend on what we assume for the value of S. Well, let's see how that works. So we just saw that the probability of the data is these two terms, these two products. Now the probability of any particular vector V given S, well, every time V is equal to 1, that's an event with probability S, and every time V is equal to 0, that's an event with probability 1 minus S. So my notation here is a little awkward. The number of powers of S we have is just the number of events we have with Vi equal to 1, and similarly for 1 minus S, the number of factors is the number with Vi equal to 0, times, of course, the prior on S, which goes all the way back to here. And the reason I'm putting up with this weird notation is because it isn't going to last very long. If there are this many factors, I can just put them inside the product here because that's exactly the number of terms in the product. And similarly, I can distribute these factors into the product here. So this is the answer. This is the complete Bayesian model for the probability of any particular assignment and any particular value of S jointly. Usually we're interested in marginalizations of this. This model with this joint probability is just too big to comprehend directly. So let's look at some marginalizations of the Bayesian model that we might want to make. For example, we might want to know what is the probability of S. S, you'll recall, is the mixture parameter. It told what fraction of the events would lie in distribution 1 versus what fraction would lie in distribution 0. So that says we're interested in S, we're not interested in V, and so we need to marginalize, integrate, or in this case, because V is a bit vector, simply sum over all possible values of the vector V. And again, a little awkward notation, I'm going to write V lies in 2 to the n, meaning all 2 to the n possible values of V. And for each such bit vector, we have our formula from above that comes up here. And now there's an amazing little thing that happens. You just have to stare at it to see. The key step is that this whole sum is simply a sum over all the events, whether they're in Vi equals 1 or Vi equal to 0, of this linear thing, and then the P of S just comes through here. How can that be? Well, you have to conceptually multiply this out for all the events. And of course you'll get, because you're going to be multiplying n terms, each of which has 2 linear pieces, you're going to get 2 to the n possibilities, 2 to the n terms in the sum, and you'll get every possibility of assigning I to either the left side or the right side in its factor as it comes along. There's a factor here for each I. So this is basically a huge multinomial expansion, but as I say, if you just stare at it and think, you'll see that the terms in this multinomial are just the sum over all the possible terms of this thing. So that works out quite nicely, and this is a simple formula that you can apply as a product over the data, if you know prior on S, for what the probability of S is. And you see it has a simple interpretation. This is the probability of event I, not in either distribution 1 or distribution 2, but in a weighted average of the two distributions, simply weighted by the mixture parameter, the fraction of events in each distribution. And then you have to multiply that by the prior on what that mixture parameter is. Here's an even more interesting marginalization. That's the one that gives the assignment of each event to one distribution or the other. So let's work through that. Suppose I'm interested in event J. and I want to know the probability that event j is drawn from distribution 1 given the data. So now what I want to marginalize over is s, the mixture parameter. So here's an integral, and then here down at this end is a p of s ds, and that's the marginalization. And then I also want to marginalize over all the components of v, the assignment vector, that I'm not interested. I'm only interested in j. So here is a sum for all vectors v in this set of 2 to the n minus 1 possibilities, that is, not assigning v sub j, but assigning all the v sub i's not equal to j. And so now what's the probability of the data that I put inside here? Well, the one that I am assigning to the value 1 is p sub j, so there's a p sub ij times a mixture value s, because I'm assigning it to 1. And then the sum, we can move the sum into here, and now we have the product over all the possibilities of vi equals to 1 or vi equals to 0 and how the data is assigned. Well, this sum and these products have exactly that same form of being, if you stare at it, a product of a whole bunch of linear factors, each with 2 terms. In fact, you'll recall from the previous slide that we defined this quantity, the probability of s given the data, as the product of all of these terms. It's a little small here, but I hope you can see it, with a p sub 1i times s and a p sub 0i times 1 minus s. And when we sum over just all of them except j, we'll get all of these terms, except we won't have one factor for j. So an easy way to write that is to write it as p sub s given the data, that's all of the factors, and then just divide out the one factor for j that we don't want to be included in the product. So that's p sub 1js, p sub 0j times 1 minus s. Now just rearranging this a little bit, you see that this has a very intuitive form. This says that the probability that the assignment of the jth thing to 1 is just the relative probability of what it would have if it is 1 compared with the sum of the weighted sum, weighted by s and 1 minus s, of its probability in distribution 1, its probability in distribution 0, and now marginalized not over a prior here, but now over a posterior, the actual probability of the mixture parameter s given the data. And similarly, the probability that vj equals 0 given the data, that it's drawn from distribution 0, just puts up here in the numerator p0j times 1 minus s. And you can see that although I've been a good Bayesian and written the proportionality signs here that come from Bayes' theorem, in fact these are properly normalized as written, because if you add this to this, you get 1 for these terms, and then the integral of the probability of s given the data, ds, is 1. So these are the actual assignment probabilities. Again, the assignment probability is just the data points' relative probability in the two distributions, weighted by the mixed probability, and then averaged or marginalized over what the mixed probability is likely to be given the data. And here's a picture of somebody, in my mind there, assigning apples to either this bin or that bin. This is a very general idea, mixture models, and it can occur with many useful variations. So it's not always exactly the formulas above, but it's the formulas above and their cousins. And speaking of cousins, let's apply the mixture model to the town family. Do you remember the town family? We last saw them in segment 15, and before that we first introduced them in segment 6. So if you have no idea what this picture means with these binomial probabilities shown in green here, and these deltas, which are numbers of mutations that the individual town people have, mutations in their variable length short tandem repeats. If you don't remember what that's all about, go back to segment 6. Here we want to come back to the one question that we didn't previously do a good job of, and that was for these outliers, these towns T2 and T11 who had large numbers of mutations in their short tandem repeats, and also this one over here, town 13, who had a moderately large number, but out of a much smaller number of tests that he paid for. We wanted to know, are these genuine towns whose descendancy is as shown in the picture all the way back to Williamtown, or are these what are called, very delicately, non-paternal events? That means that, for example, in this one, somewhere along his line, there's an individual who is not actually the son of the indicated father here. So I like to call this Bayes and bar sinister. What's bar sinister? Well, it turns out in heraldry in medieval times and even extending into modern times, if you were the bastard son of a nobleman, well, that's not quite as good as being the legitimate son, but it's still something that you would be proud of, and you would have a coat of arms that shows who your true father and mother are, and it would have this bar pointing downward to the left here. Sinister is Latin for left, and the bar sinister would show that you're the bastard son, not the legitimate son. So this particular one is the coat of arms of Sir Charles Beauclerk, the first Duke of St. Albans, bastard son of King Charles II by the famous actress Nell Gwynn. But back to the town family. We can now understand that the town family problem is really a mixture model problem. Each variable length short tandem repeat sample either comes from a descendant of Williamtown as indicated on the chart, or it comes from a descendant of the true father, a non-paternal event, just somebody else. And we're given an unknown mixture of such samples, the towns down at the bottom of the family tree, and we have an assignment problem. We want to assign each town either to the true descendant component or to the non-paternal event component. So let's see how we do that using the formalism that we've just developed. Our model has three unknown parameters. The first of these is exactly the parameter that we saw before in segments 6 and 15. It's the mutation probability per locus per generation. Now we also need a new parameter. This is going to be analogous to the mixture parameter S that we saw previously in the workup. Here we're going to call it C, and it's going to be defined as the non-paternal probability per generation. So C is the probability, if I'm a town, that I'm not my father's son. Now, because we also need to know something about this other mixture component, the one which is non-paternal, we're going to model that in a very simple way by a single parameter L. And L says, if it's a non-paternal event, well, how many generations is it back to the last common ancestor? The idea here is we all have a last common ancestor. All humans are cousins to some degree, and we don't know exactly what, on average, in this little town in England, the number of generations back you have to go before you get a last common ancestor. So we're going to model that as a Bayesian parameter, and then, of course, we'll usually be interested in marginalizing over that parameter. This is not a very accurate way of doing this. Modeling L is exactly some constant number of generations, 75 or 10 or whatever it's going to come out. But it will illustrate the point of mixture models. If it really mattered, we could come back and do a better job of modeling L. And at the end of this segment, I'll show you how to do that. So here's the model. I'm going to write it down in MATLAB instead of in equations, but you can see what it is. The fundamental mixture thing, which I'm going to call P-mix here, is a mixture of two binomial probabilities, just like the ones that we modeled before. Here's the first in the mixture, and here's the second in the mixture. And they're mixed with relative weights that are given by this C parameter. But not exactly C by itself. How does that work? Well, here's the binomial that's the probability that you are your father's son. It says that the number of mutations k that you've accumulated is just what you would expect by going n generations with a certain number of loci and a mutation probability per generation r, one of the parameters. And that occurs with the probability that your entire line is correct. So since in each generation there's a probability c of a non-paternal event, that means there's a probability 1 minus c that you are your father's son. And since that must be true for all n generations, we take 1 minus c to the nth here. On the other hand, this binomial probability substitutes for the number of generations, not n, but n plus LCA, last common ancestor, a much larger number of generations, and same number of mutations, because that's what we observe. And this enters the mix with probability 1 minus the probability here, that is to say 1 minus c to the nth power. Now the model, just as in our previous treatments of the town family, is a product of factors. There's not exactly one factor for each town, because you'll recall we had to unravel some dependencies. But now the factors, instead of being pure binomials by themselves, are these mixture probabilities with the unknown parameters r, c, and LCA. Here's the overall prior, the non-informative prior on the mutation probability per locus per generation, and you'll see I took that to be log uniform rather than uniform, again, as in the previous segments. Notice that now in this model we're not trimming any data. That's the whole point here. It's a mixture model and we can include all the data. So that's why we have a factor with 23 mutations here. And then down here we have a factor with 4 mutations but in only 12 loci here. It's the entire data set. Now on the slide after this one, I'm going to show you the MATLAB program to sort this all out. And it really comes out very short when you use the proper MATLAB functions. So let me just mention to you that if you don't know what these MATLAB functions are, you might pause the tape and read the little descriptions here, or you might go back and look them up. ndgrid is a function that if I'm given a bunch of values of a variable x, a bunch of values for a variable y, a bunch of values for a variable z, it makes a grid of every possible combination of the x, y, and z values ordered geometrically in the logical way. ArrayFun is a function that takes any function and applies it to each element of an array. And then squeezed in on the right here, that may be a little too cute, is the function squeeze, which simply takes an array that has one dimension whose length is only 1 and removes that one dimension from the array to make an array of lower dimensionality, but it's actually the same array. It has exactly the same components as it did before. Squeeze, when you have to use it, is a little bit of an annoyance in MATLAB, as you'll see on the next slide. Here we go. So we're going to evaluate our model over a three-dimensional grid of parameters, because these are the parameters that we might want to marginalize over. So we're going to choose a set of possible values for r, the mutation probability, and those will be equally spaced from 0.0005 to 0.02 in steps of 0.0005. We're going to take a set of interesting values for c, the probability per generation of a non-paternal event. So just to span a big logarithmic range, let's try values of c 2 parts in 1,000, 5 parts in 1,000, 1%, 2%, 3%, 6%, a tenth, and 20%. You might think about what you think in normal human relations in a little town in England the probability of non-paternal events actually is. Do you think it's as small as 2 parts in 1,000 or as large as 10 or 20%? That's a problem in sociology, not a problem in statistics in this course. And then for last common ancestor, how many generations do you have to go back to get the last common ancestor? Well, I'm going to try just 4 values. I'm going to try 25 generations, 50, 100, and 200 generations. So now here's all we have to do. We use that ndGrid function to take these arrays of interesting values and make a grid. I should mention here where the priors have gone. When I make this grid, it's a grid of boxes, one box for every combination of choosing an R value, a C value, and an LCA value. And what I'm implicitly going to assume is that the prior is uniform over the cells in that box. That is to say, the priors on these variables each separately are approximately uniform in a logarithmic range here or a linear range here around each central value. So the priors have kind of disappeared explicitly in the calculation, but are still there implicitly in how I do the gridding. Each cell has an equal prior. So now it's really easy. I simply take the model, which you'll recall was a function of R grid of R, C, and LCA, and use ArrayFun to apply that model over the array that I got out here from ndGrid of every possible value of R, every possible value of C, and every possible value of LCA grid. Now, that's the Bayesian numerator. The Bayesian denominator is simply the sum over all of the cells in this three-dimensional array, and I renormalize the values here by dividing each of them by the sum. The reason for these 2's in the names is that this model, if you look on the previous slide, was named Model 2. That's because it's the mixture model with 2 components. So this is the answer. This is the probability of each grid cell. Of course, we're not interested in any particular cell, but we're interested in marginalizations of it. And marginalizations now of this discrete grid are simply sums over it. So if we're interested in the distribution of mutation probabilities per generation, we just take the whole grid and we marginalize by first summing over dimension 3, which was the LCA vals, and then we sum over dimension 2, which was the C vals, and then that just gives us a distribution over the R vals. Similarly, if we're interested in the distribution of probability of non-paternal events, we have to sum over 3, and then we have to sum over 1 to get rid of the R vals, and we're left with a distribution over C. And finally, if we're just interested in the distribution of that parameter last common ancestor, we have to sum over R vals and C vals. Well, if you try to do that in MATLAB, it complains because of you're doing dimensions in the wrong order. It's reduced a dimension, so you have to use this unfortunate squeeze, and these indices aren't what you think they would be. It sounds like that's a trap that you could get wrong, but it's actually pretty easy to figure it out. Here's a hint. Use the size function to debug when you do a sum of something, whether you've gotten the array dimensions that you expect, and if you don't, then figure out where you have to put in the squeeze function. Okay, and then finally I'm just going to plot these 3 marginal distributions here. So the first one, which is the one that we've previously plotted, I've plotted in green the distribution of mutation probabilities, so that's here. In previous segments when we did this, we got the blue curve, and you'll see that now, because we've included the tails, even allowing that they may not be actual descendants of William Towne, nevertheless, including them pulls this distribution to larger values of mutation probability, as it should properly do. So this is probably very likely a better estimate of the mutation probability than our previous estimates. But now what we're interested in are the other 2 marginalizations. So here's the probability of a non-paternal event per generation. It's on a logarithmic scale. It's pretty broad, but you'll see it peaks at a value of a few percent. I don't know if that's what you guessed, but that's how it comes out for this particular data set. And then you can also see that we determine a typical value for the number of generations back to the last common ancestor in the village in England that Williamtown came from, and that comes out to be about 100 generations. Well, if a generation is 20 years, maybe back then, that's 2,000 years. That's probably reasonable for the amount of time that people with a common ancestry have been living in this part of England prior to the year 1600. So the model works. Finally, what we're interested in calculating, of course, is the assignment probabilities. What's the assignment of a particular town to either the true descendants of Williamtown or false descendants? Here's another one of these coats of arms, bar sinister, of bastards. I like this one because on the bar sinister there are anchors. I think that's because father was a sailor who wasn't in port for very long. But let's go on with the town family. So we're going to define a function that's going to be the non-paternal probability. Let me show you what that function really is. Here, this inner function, p pat, you'll see is just the here the inner function p pat here basically computes this term up here. You'll see that what it does is it computes either one binomial probability or another binomial probability with these proportions, the 1 minus c to the n or the 1 minus the 1 minus c to the n. For some reason here I switched over to using the Poisson probability distribution instead of the binary probability distribution, but as we've seen before, that's a good approximation to it, so that really won't make any numerical difference at all. It's probably just a conceptual bug on my part. Here what we do with this inner function p pat is we apply it across the entire grid of RC and LCA values. That gives a grid of all of these things. We multiply it by the analog of the probability of S given the data. But now we have not just a single marginalization over ds, we have these three marginalizations over R, C, and L. Nevertheless, the probability that goes here is that probability over the grid that we computed here. And then the analog of this integral ds is now three sums, summing over 3, 2, and 1, all three dimensions, and then to get that down to being a scalar you have to do a squeeze function on that. Now I could just compute this probability separately for each of those 12 townses, but instead, because I think we'll learn a little more, I'm going to plot it as a function of how many mutations k an individual has, and how many generations, either 9, 10, or 11, they claim in descendancy from Williamtown. And then we'll just see how the probabilities vary with k, the number of mutations in those three cases. So that's what's shown right here. Here's the non-paternal probability from that function, from 0 to 1. Here's the number of mutations, k. So you'll see the ones that there's no question about, T6, T3, T8, T4, T5, their non-paternal probability is essentially 0. But you'll see that when you get up to 6 or 7 or 8 mutations here, the non-paternal probability very rapidly rises. That's 6 or 7 or 8 out of 37 loci. Now, T13 was an exception. He's the one who didn't have 37 loci, so we'll actually go in and numerically use our little function here for the values for T13 and compute that he has a non-paternal probability of 85%. He's pretty likely not a town descendant. T11 was the interesting one because T11 was the one with 5 mutations, and you see that by this mixture model, T11 has fought his way back to legitimacy. It does seem that within this model, his probability of being a descendant of Williamtown is quite good, well under, for example, the p equals 5% significance test level. So I guess this is a happy ending as far as T11 is concerned. T2, this one with 23 mutations, there's no way to possibly save. Now I have to tell you this picture is not quite right because I found a bug in my code. I don't think it actually affects what it looks like qualitatively, but I'll challenge you to redo the calculation and see what picture you get. Let me mention here something very important called hierarchical Bayesian models. It's something that perhaps we'll do in a later segment, but it comes in right here on this issue that our model for LCA, the number of generations to the last common ancestor, was too crude. In fact, although we're declaring that T11 is legitimate within the context of the model that we worked out, I bet that he's not. I bet that what T11 really represents is a non-paternal event with a distant cousin, but not all the way back to the last common ancestor of the entire village. So how would we model that if we really wanted to? I'm not going to do it in detail, I'm just going to give you the idea here. So our old model had a fixed value of L, that's what we called LCA in the code on the previous slide. And the mixture probability was a mixture between a binomial probability with some number of generations and a binomial probability with n plus L generations. And notice that L had the same value for every single town's individual, so that the final probability of the parameters given the data contained factors, each of which depended on L, this constant. Now a hierarchical model would say each town is allowed to have a different value of L. If he's a non-paternal event, then there's some number of generations back to where he rejoins the town descendancy, and therefore his number of mutations should be different only by something reflecting that different, perhaps much smaller number. Now you might think that this adds just a huge number of parameters to the model if we're going to allow each town, if he's illegitimate, to have a different value of L. But the hierarchical model says no. The value of L is drawn from some distribution, perhaps a gamma distribution, that has just a couple of parameters, alpha and beta. And then the probability of all the parameters, including alpha and beta, the parameters of the gamma function, given the data, are, as before, a product over all of the towns in the usual way. Now each town is given his own value of Li, but that value of Li occurs only with the probability of its own distribution up here. So we get the gamma probability of Li given the parameters alpha and beta. And now the key point is we marginalize the integral here and the dLi here over all of the individual values of Li, leaving in the model only these hyperparameters alpha and beta. Of course we need to have a prior on everything RC, alpha, and beta. So what makes this model hierarchical is that Li is a parameter in one piece of the model, namely in this inner piece here, but it's a draw from a distribution in a higher piece in the hierarchical model, namely the part that tells what is the distribution of L's. And the higher part is where the dependency on these hyperparameters alpha and beta come in.